Okay, so next we are going to see the notion of functions. In calculus, just like in other areas of mathematics, we are mainly concerned with functions besides sets, of course. So we motivate the definition with these two simple examples. The temperature at which water boils depends on the elevation above sea level. This you probably already know. As we go up, the boiling point drops. It's because when water boils, the molecules in water, besides overcoming the intermolecular attraction that the molecules have among themselves when the water is in liquid state, the molecules also have to overcome the atmospheric pressure, because the atmosphere is there above the body of water or the container of water wherever the water is kept. So that is pressing down on the body of water, so it becomes somewhat difficult for the molecules to leave. And now if you take that body of water at a height above sea level, then you have less atmosphere above it, so less atmospheric pressure, so it becomes easier for the molecules to leave the body of water, so boiling point drops. The boiling point drops as we ascend. Another example is this: the interest paid on a cash investment depends on the length of time for which the investment is held. The length of time the investment is held. So we see that in each case a variable quantity depends on the values of another variable quantity. In the first case, the variable quantity is boiling point. It depends on the elevation of water, okay, elevation of the body of water above sea level. In the second example, the variable quantity is interest paid on a cash investment, and another variable quantity on which it depends is the length of time for which the investment is held, the money stays invested. So that's what we say. In each case, one variable quantity, or in each case the value of one variable quantity, which we might call y, depends on the value of another variable quantity. Which we might call x. Now since y is determined completely by x, so we say that y is a function of x. Since the value of y is completely determined by the value of x, we say that y is a function of x. For example, if we know the elevation above sea level, that tells us what the boiling point is. By some rule, there is some rule. Just like that, if we know the length of time for which an investment is held, we know exactly how much interest is going to be paid on that investment. So here x is elevation, y is boiling point. Here x is length of time for which an investment is held, cash investment, and y is interest. So in these cases, y is completely determined by x. When you have one value of x, that tells you the corresponding value of y. So in this situation, we say that y is a function of x. The letters, although we are saying we are calling the, you may call the variable on which the other variable depends an independent variable, because the length of time for which the investment is held, that can be anything depending. So that is an independent variable, it is varying as it wishes. Now the dependent variable depends on the independent variable for its value. The interest depends on the length of time for which the investment is held. So the interest is a dependent variable and the length of time for which the investment is held is an independent variable. Just like that, elevation is an independent variable, and depending on the elevation we find the boiling point. So the boiling point is the dependent variable, y is the dependent variable and x is the independent variable. But we are not going to always call them x and y. We can use other letters also depending on the situation. So the letters used for variable quantities may come from what is being described. Yes. For example, when we study circles, we usually call the area A. and the radius r. Since in fact we know a relation between a and r, we know a formula that links a and r. A is equal to pi r square. We say that a is a function of r. So if a circle has radius r, then its area is equal to pi r square. The radius in this case is an independent variable and the area of the circle is a dependent variable. So because the area is completely determined by the radius or completely determined for the radius by this formula, so a is a function of r. The dependent variable is a function of the independent variable, and the thing we were saying about the letters, it's that we won't always use x for the independent variable and y for the dependent variable. This is much natural, much more natural. Of course, you can also call the area of the circle y and the radius x, but this is more natural to call the area a and radius r. It is suggestive. Okay, so other letters can also be used. So that's what we mean when we say that the letters used for variable quantities may come from what is being described. Area and radius, so a and r. The equation a equal to pi r square is a rule that tells us how to calculate a unique output value of a for each possible input value of the radius. How to calculate the unique means single, one thing, a unique value, the unique value of a for, or unique output value, are they saying output? Yes, the unique output value. I don't want to miss any words that the authors are saying, because there may be something hidden in those words themselves. Okay, so the unique output value of a, how to calculate the unique output value of a for each possible input value of the radius r. So the formula linking a and r tells us exactly what value of a we will get for a given value of the independent variable r. So it's like the r is an input into the formula and a is an output that we get from the formula, or the output given by the formula for that particular input. One more thing that you note here is that how to calculate the unique output value of A for each possible input value of the radius r. These words have meaning, they are there for a reason. It will become clear. The set of all possible input values of the independent variable, of course, input values for the radius is called the domain of the function. Possible input values. Is there any impossible input value? Of course there is, because for us the independent variable or the input r, it is the radius of a circle. So it can take positive real values, it can also be 0, but it cannot be negative. It can never take a negative real number value. It does not make sense for a circle, for example, to have radius -1. Okay, so that's why the possible input values for r are non-negative real numbers, and the set of all possible input values is called the domain of this function. The domain is the set from where the inputs are coming. The possible values for the independent variable are coming, and the values that we get for the dependent variable, they form the range of the function. Okay, so these are some terms related to a function. The set of all output values of the area A is called the range of the function. Note one thing carefully, although we are saying the function, a function, it has not been made clear yet what the function actually is. What is a function? Is the function the dependent variable, or is the function the independent variable, or is the function the rule that links the dependent and independent variable? We will see that. Okay, let us now, before we go to the next paragraph, let us see one thing. Suppose you have the domain here and the range here. These are sets, right? We have said what they are. The domain is the set of all possible input values. For this particular example, the radius, and the range is the set of all output values, that is all the possible values for the area. Now, for each value of r from the domain, from, of course, always from the domain, nothing can be from outside domain, because then the function may not make sense. So for each possible value for r, there is a unique value for a, which is obvious, because for a given radius there is only one area for the circle that has that radius. but it will not be so obvious when we consider general functions, okay, where y can be any dependent variable and x can be any independent variable. There we have to explicitly state that for each value of the independent variable there is a unique value of the dependent variable. Not only is the dependent variable completely determined by the independent variable, but the value of y for a given x should be unique. For a given x there should be only one value of y, then only we can say that y is a function of x. Let me give you one example. Instead of these things, these examples, if someone says, say, the relationship between y and x is this, y square equal to x. Now, if you put a positive real number in place of x, say x equal to 4. Keep in mind, x is the independent variable and y is the dependent variable. So y will be completely determined by x. Okay, now if we take x equal to 4 and we are saying that y is a real number, then there are two values of y actually for which this equation is satisfied. So for this single value of x, these are the two values of y, -2 and +2, the squares of both of which are equal to 4. So this if this is the relationship between y and x, then we won't say that y is a function of x. So that's why this uniqueness of the output value is important for each possible input value. Okay, so that's what we wanted to stress here. Now next, before we go to the next paragraph, this still continues. Now, if for this particular function which links area and radius, what is the input? What is the domain? What are the possible values for the radius of a circle? As we have already said, the radius can be any positive real number or 0, but it can never be a negative real number. And so is the case with area. Area of a circle can be a positive real number or 0, but never a negative real number. So that's what the authors say, since circles cannot have negative radii or areas, the domain and range of the circle area function are both this interval. The domain and range of the circle area function. We can call it the circle area function because it calculates the area of a circle and depending on its radius, are both this interval, okay, which consists of all non-negative real numbers. Now one thing is of course clear, because the independent variable, the radius, can take either the value 0 or any positive real number. Okay, and area is also either 0 or a positive real number. But what is immediately not clear is whether every non-negative real number appears as the area of some circle. That is a question. In fact, it does, which can be seen quite easily. You see, suppose you choose, because otherwise you see, what are we saying here? We are saying that the set of all output values of the area A is called the range of the function. That means that when this is our function, right? You put one value of r, say r equal to 0, you get one value of a is equal to 0. You put another value of r, some positive real number, you get a corresponding a. Another r, you get a corresponding a. All those a's, say you put r equal to 0, you get a naught, which is 0 itself. Let me show some of them. You put some positive real number r1 here, you get some area a1. You put another positive real number r2, you get an area a2, and this goes on and on, because there are infinitely many possibilities for r, correspondingly there are infinitely many possibilities for a. So all these area values taken together form the range of the function. All the output values, the set of all output values of the area A is called the range. How are we saying that this set is actually equal to this interval? Of course, this set is contained in this interval as a subset, because each area is either 0 or positive. But does every non-negative real number appear as the area of some circle? To see that, you choose any non-negative real number. Say you choose anything, say you choose alpha. Alpha is a non-negative real number. Is alpha the area of some circle? If so, what is the radius of that circle? Note that since alpha is a non-negative real number, so square root of alpha exists, and that is also a non-negative real number. And in fact, square root of alpha divided by pi exists, because alpha is a non-negative real number. If you divide alpha by pi, that is also a non-negative real number. So its square root exists and is itself a non-negative real number. The non-negative square root, of course, not the negative one, because there are two square roots, right? This exists and it is also a non-negative real number. Now, if someone considers a circle with radius equal to this, then what happens? What is the area of this circle? Say the circle has radius r prime. Then the area of this circle is a equal to, let us write it here, a equal to pi r prime square. So this is pi times square root of alpha divided by pi square. After simplification, you see that this is equal to alpha. So yes, not only are all the areas that we get for the circles non-negative real numbers, but in fact every non-negative real number appears as the area of some circle. So the range is not only a subset of this, the range is in fact equal to this. So that's why they are saying that both the domain and the range are equal to this interval, the set of all non-negative real numbers. Okay, so that is the notion of the domain and range of a function. Okay, now we come to a general function. The domain and range of a mathematical function can be any sets, not just sets of numbers, can be any sets of objects, or I think I should have written sets of any objects, or same thing, any set of objects. They do not have to consist of numbers. If you are wondering how such functions look, where neither the input nor the output is a number, then we can give such an example. For example, if we can of course give an example where we have an abstract function, but that will not be very appealing to you at this stage at least. Instead, let me think of a function which does not involve numbers but somehow is, this is open, but somehow still it feels like a function. What can I possibly say here? Which is entirely non-mathematical in a way that it does not involve numbers or vectors or things like that. You can think of a function like this. Say we have a function that gives you the days of a week that start with the letter T. Okay. Then the domain of the function of that particular function consists of all the days in the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday and Saturday. This is the domain, and it gives us those days whose names start with the letter T. So the range is Tuesday and Thursday. This is also a function. For each oh no, this is not making sense. No, this is not making sense. What I wanted to say, we cannot say Tuesday and Thursday like this. I think you can try to see what I am trying to do here. I want to define a function, or instead, okay, let's just leave this and instead define a function like this. Say we have the set of these letters and we have some more letters E, F, G. Okay, when and this is the domain of my function and this is the range. When the input is, there is a variable, that variable takes these four values. Unlike this case where the variable r takes, the independent variable r takes infinitely many values, here the independent variable, whatever it is, since we are denoting it by this generic symbol x, so x can take the values a, b, c and d. When x is a, we agree to say that the value of y is e. Just like x, y also takes these three values. When x is b, again the value of y is e. When x is c, the value of y is f. When x is d, the value of y is g. I know this looks extremely strange, and it's that's why I was saying it won't be that appealing to you, but I can't at this moment think of something immediately that involves some real life situation, and also it's a function that does not involve numbers or vectors or any other mathematical thing. Okay, the point here is that for each value of the independent variable, there is a unique value of the dependent variable. It's like you are putting the value x equal to a in the function, and the function is giving you the output y equal to e. So when your input is a, your output is e. When your input is b, then also the output is e. Note that for each value of x, there must be a unique output. For two different values of x, you may get the same output. That is not a problem. But once you choose one single value of x, for that you should not have two outputs like what we had there. For x equal to 4, we had two values of y, -2 and +2. That should not happen. From the domain, from a single element or from a single input, only one arrow should go out, not more than one arrow. Okay, so the output for a single value in the domain should be unique. And so this is a function that does not involve any numbers. So the domain and range both are just general sets which have some elements. Okay, so they do not have to consist of numbers. They can be any sets of objects. But the thing is that the functions with which we will deal, mainly they will involve numbers, because we will use that type of functions only in calculus. Most of the domains and ranges we will encounter, most of the domains and ranges we encounter in this book however, will be sets of real numbers. Okay, so in this book at least we won't see this type of functions, but keep in mind that the mathematical definition of a function is not just about putting a number as an input and getting again a number as an output. It is more general than that. The input that you give can be any object, the output also can be any object. Okay, next, in calculus we often want to refer to a generic function without having any particular formula. In mind, unlike the circle area function where the formula a equal to pi r square exactly tells us how to calculate a unique value of a for a given value of r, but that's not always the case. Sometimes we want to refer to a generic function without having any particular formula in mind. For example, a function like this. What formula can you think of when you want to get e from a and e from b? We cannot think of any formula. The point that this is also a function simply lies in the fact that for each element in the domain there is a unique element in the range to which it is related by that function. So that's why when we said that in this formula, when we asked what is actually the function in this formula that links a and r, we could have said that this equation itself is the function which tells us how to link r and a, but that is not entirely true, although that is true in this case, but in here we don't have a formula. So the function is simply this rule itself that tells us what the output is for a given input. That's it. Okay, so in this case, so you see that pictorially we have simply shown the association using arrows, but definitely we need some sort of notation that will link x and y, the independent variable and the dependent variable, in a general way which will tell us that y is a function of x. And the symbolic way was given by the mathematician Leonhard Euler. The Swiss mathematician, extremely famous and prolific mathematician, although the spelling is E-U-L-E-R, but it's pronounced Euler, okay, not Euler. Many people wrongly say Euler, but that is incorrect, it's Euler. And the way of writing, expressing that y is the function of x is this. Euler invented a symbolic way a symbolic way to say y is a function of x. To say this thing by writing a symbol like this. Okay, and this itself is read as y equals f of x. That's how we read it when we see something like this. Y equals f of x. Y is a function of x. Okay. And the f we see here, just like x and y, is not fixed. The letter f is not fixed. In fact, sometimes we will use other letters also, particularly when more than one function is involved. Like say y is a function of x. Y can be a different function of x also, although we have to of course write something else in place of y and something else in place of x. Say we want to say that the dependent variable y is a function of x, so we write y equal to fx. We don't really know what this function f is, but there is some function. At the same time, there is another dependent variable y prime depending on another independent variable x prime. We want to say that this is also a function of x. Then we won't write that f because it represents the same function. Instead, we will use some other letter, g. This also tells us that y prime is a function of x prime. This way of writing this notation makes y prime a function of x prime. That is the convention. When we write an equation like this, we have to understand that the independent variable is x prime, the dependent variable is y prime, and there is a function that links these two variables. Okay, so that function sometimes is named f, sometimes is named g, or whatever you may use. In this notation, you may look up Leonhard Euler on the web. You will see many things about him. Okay, he became partially blind, or I think totally blind towards the end of his life. But he found so many things that even after his death, it took many years to publish them all. I think 70 or 75, I can't remember the exact figure, volumes were needed to publish all his works entirely, completely. Okay, so where were we? In this notation, the symbol f represents the function. The history is very interesting. Euler wanted to study physics, but the Bernoulli brothers brought mathematics to him, or brought him to mathematics. Okay, they introduced him to the works of because there are so many Bernoullis now, it becomes difficult to remember which Bernoulli brothers I am talking about. But you will see in the history of Leonhard Euler and his works, you will see that the history is very interesting, just like other historical parts of mathematics. So in this notation, the symbol f represents the function. The letter x, called the independent variable, the letter x independent variable represents an input value. From the domain of f, because from the domain only the values of x will be chosen, and the letter y, called the dependent variable, called the dependent variable represents the corresponding output value. Output value f of x. Whenever we see this symbol, don't read fx, okay, always read f of x, the f value of x, or the functional value at the point x represents the output value f of x in the range of f. So this statement contains everything about the function. The letter x, called the independent variable, represents an input value from the domain of f. From the domain, the values of x will be chosen, and the letter y, known as the called the dependent variable, represents the corresponding output value, which is nothing but f of x in the range of f. Now, having discussed all these things, now we give a formal definition of a function, which actually does not involve any formula, but it's more like that a, b, c, d, e, f, g, that example. So this is the first definition of this chapter. Although the definition of a function can be given much more generally than what we are going to write here, but for our purposes this definition is enough, where our domain and range, they are going to be sets of real numbers. In general, as we have seen or we have discussed, the domain and range of a function can be any set. A function or have they defined it in general for any sets. I think they have given the okay, it's not just for real numbers. The definition given here is in fact the general definition. Okay, fine. Now I mistook it for something else. A function from a set D, which is any set, to a set R is a rule that assigns a unique element f of x in R to each element x in D. In this definition, the set D, which is also written as this, and this is read as D of f. Just like f of x, we read this as D of f, is the domain of the function. Is the domain of the function f, and R is a set containing the range of f, not necessarily itself the range of f. Okay, so this definition is a little different from what we have been discussing. Okay, before this definition. Before, what we discussed is this. Say we have the function a equal to pi r square. For this function, we determined that the domain is the set of all non-negative real numbers, and the range is also the set of all non-negative real numbers. For any non-negative real number r, there is a corresponding non-negative real number a as the area of the circle whose radius is r. So in this description of the circle area function, the sets involved were the domain of the function and the range of the function. Here, however, the domain is there, but R seems to be something else, something other than the range. Let us see what the definition says. A function from a set D to a set R is a rule that assigns a unique element fx. Uniqueness of the value of the dependent variable is still there in R to each element x in D. In this definition, this D, which also is written sometimes as D of f, to denote the fact that it is the domain of f, is the domain of the function f, and R is not necessarily the range. R is a set containing the range of f. So the circle area function we have here, you can also write the circle area function like this. The circle area function, in fact, let us just write it extra, it's not there in the text. The circle area function f is a function from this to say R, the set of real numbers, whose rule is given by a is equal to pi r square. If we want, we can we have in fact actually given the function a name f. So this a is equal to pi r square is actually a equal to f of r, where a has taken the role of y, the dependent variable, and r has taken the role of x, the independent variable, and f r is pi r square. Okay, so that is the formula or the rule which tells us how to link the independent variable and the dependent variable. Now note that unlike what we previously had, we are now defining the function from this set to the set of real numbers. This is not, of course, equal to the non-negative real numbers. This is a set that contains the range inside of it as a subset. Okay, so and this second set can be anything. You just have to make sure that the second set is large enough to contain all the outputs inside of it. You can in fact take the second set to also be this itself. But it should not be smaller than this, in the sense that you remove some non-negative real number, then the area function cannot be defined properly. Okay, so all the outputs should be there inside the second set, and we don't usually give any name to the second set. For us, the domain is there, that is in fact I should not say that is the set of all possible inputs, although we are discussing it like that the domain is the set of all possible inputs, but you can shrink the domain. You can choose to not consider all the possible inputs, but rather a subset of all the possible inputs. Just like here, instead of considering the set of all outputs, you may choose to consider a larger set for the second set. Okay, so the domain is there and the second set is there. The second set, however, should contain all the outputs, all the possible outputs for the given input. The absolute largest possible set of all inputs for which this formula makes sense, that is called the natural domain of the function. You, instead of taking that largest possible set, you can in fact take a smaller set as the domain. You will technically get a different function. For example, instead of considering all possible circles, you are say considering circles whose radii are all positive integers. Okay, then clearly this is not the domain. The domain is the set of all positive integers. So that again, for that also you have an area function, and that function technically is different from the actual area, ordinary area function, circle area function. For the circle area function, which is given by this rule or this formula, the natural domain is this, which is the largest possible. Any subset of it can also be considered as the domain. Okay. In the beginning these things may seem somewhat confusing, but as we become more and more familiar with them, they will become more and more natural, just like any other thing. So there is a pictorial representation of a function like this. So this is D, which is the domain set, and this is R, a set containing the range. That is a set of which the range is a subset, or more simply a superset of the range, okay, which may or may not be equal to the range. So for points in the domain, or for elements in the domain, there are elements in the range to which these are associated, or more simply, for every input there is a unique output. For every input in the domain there is a unique output in the range. The range, actual range of this function is a set which is a subset of R. It may be equal to R, it may be smaller than R, okay. And there is another, since we are saying input and output, the function also can be thought of as a machine. Think of a function f as a kind of machine. That produces an output value fx in its range when we feed it an input value x from the domain. There is in fact a picture also. It's like this is a machine, the function. From this side we give an input from the domain. The domain is like a warehouse of raw materials. We put the raw materials in the factory, and the factory produces some finished products or goods which are outputs in the range. So the range is the warehouse that contains the finished products before they are shipped or before they are sent to the stores for customers to buy. Fx, so that is the output which belongs to the range. In this book, we will usually define functions in one of these two ways. in one of these two ways. Number one, by giving a formula. Such as y equal to x square, that uses a dependent variable y to denote the value of the function. Or I think I need to refill. Or 2, by giving a formula such as fx equal to x square, that defines a function symbol f to name the function. So mainly in these two ways we will define a function. So that circle area function that we defined, a equal to pi r square, that has been defined in this first way, okay, where we did not bother to give the function itself any name. But if we say want to name the circle area function f, then we would define f of r equal to pi r square, okay, for that particular function. So that is the second way. In the second way of defining a function, we bother to give the function a name. In the first way we don't. That is the difference. Strictly speaking, we should call the function f and not fx and not f of x, as the latter denotes the value of the function at the point x rather than the function itself. call the function f and not f of x, denotes the value of the function at the point x. You see why we are making this statement. We said that this equation defines a as a function of r. This sentence itself makes us think that a is a function of r means a itself is the function. Actually, that is not true. It's just a way of saying that a is a function of r. When we say a is a function of r, we really mean that there is a function which links the independent variable r to the dependent variable a in such a way that for each element or for each input value of r from the domain of the function, there is a unique output value of a in the range. A itself is not the function. The function is there in the background, which this formula does not name. It's like expressing the function in this way. So that's why we are saying, strictly speaking, we should call the function f and not f of x, because if we gave it a name, say f, then we would write like this, no? A is equal to f of r, where f of r is pi r square. Then you may think that a itself is the function, but that is not true. The function is there in the background and a is one particular value of the function, namely the value, the output value when the input value is r. So as the latter, fx denotes the value of the function at the point x. Okay. But the confusing thing here is this. However, I can't seem to be able to write tonight. However, as is common usage, we will often refer to the function as fx in order to name the variable on which f depends. Or we will call the or we will refer to the function as fx. Instead of strictly calling it f, in order to name the variable on which f depends, namely the independent variable. So ideally we should distinguish between f and fx. F is the function, fx is the value of the function, but normally we don't do so. In the circle area function, if you want, you can call a itself, you can think of a itself as the function. Okay, although strictly speaking, a is a value of the function. it is sometimes convenient to use a single letter to denote both a function and its dependent. Okay, so this makes things even more confusing. But see, at one go, of course, you cannot, if you are seeing these things for the first time, at one go you cannot digest all the things. You have to see this video again and again, work with the examples, try to solve the problems. Only after a certain amount of time, when you gain sufficient familiarity and experience with these things, then only the things will start to make sense. For now, let us just go through all the things, and then it will depend on you how much time you spend with these things. It is sometimes convenient to use a single letter to denote both a function and its dependent variable. What that means? That means that, for example, instead of calling the area function as the function f, you can see here that the independent variable is r, the function name is f, and the dependent variable is a. Instead of using these two letters to denote the dependent variable and the function, one can, if one wants, use the same letter to denote both the function as well as the dependent variable, which actually matches with this casual way of treating the function as well as the dependent variable as the same thing. Okay, so if we are thinking of fx itself as the function, although strictly speaking it's actually the value of the dependent variable when the independent variable is x, so we may as well use the same name to denote both the function as well as the dependent variable. That's what the author is saying here, or rather the authors are saying here. For instance, we might say that the area A of a circle of radius r is given by the function a equal to a of r, or in fact instead of writing that much also, we can write a of r equal to pi r square. So those two ways of writing a function, that 1 and 2, we have followed the second way here, where we write say fx equal to x square. In that way we have written this. So here a denotes both the function as well as the dependent variable in the circle area function. After this we have evaluation of functions, how one actually calculates a value of the dependent variable when a value of the independent variable is given, and then what is that natural domain, the largest possible domain that we were discussing there, and then what the graph of a function is. The graph of a function is something that you have already come across. You already have been asked to draw the graph of this function, say y equal to x square or y equal to 2x plus 3. So we will see those things, but in the next part, in the next video on this. So until then, it's me, Lucifer, from a mathematical room. So see you in the next calculus video. Have a nice night.